We're going to do a few more examples of relative extrema, finding the relative minimum and maximum points. We did some easy ones last time. We're going to do some this time that are less easy. Let's just get to it. All right, first example. We're just going to do 2 examples today, that's all. First one is x squared e to the x minus 3. Your job is to find all relative extrema, and for each one say if it's a minimum or a maximum. Find and identify. All right. I hope you remember the procedure here. You take the derivative, simplify as much as you can, find the critical numbers, make that chart, and then you look at, like, does it go plus to minus or minus to plus? That's how you tell if they're minimum or maximum. Let's do it. We begin by taking the derivative. All right, what do we got here? I got, first of all, 2 things being subtracted, right? There's this part and that part. This part is a product, so I'm going to have to use the product rule here. The second part is just a constant, so it's going to become 0 when you take the derivative for that stuff. So this minus 3 actually will just disappear entirely. The entire derivative will be about this x squared e to the x. And we got to do the product rule. It is the first thing times the derivative of the second thing plus second thing times derivative of the first thing. So first thing is x squared. Derivative of the second part. Remember what is derivative e to the x? I hope you remember. Derivative of e to the x is e to the x. Okay? Plus second thing times derivative of the first thing. Second thing is e to the x. Derivative of the first thing is 2x. And then the minus 3, like I said, becomes 0 because it's a constant. All right. This is the derivative. We should simplify as much as we can because it will serve us well later on. Both of these things have e to the x in them, so I'm going to factor out e to the x. Actually, you can also factor x from both of them. So I'm going to factor x, e to the x, and then what's remaining here is just x, plus what's left here is 2. All right, this is as simple as this derivative is going to get. That's the factored form. Let's find the critical numbers then. So this is f prime of x. The critical numbers, recall, are when the derivative equals 0, or when the derivative does not exist. Now, in this example, this always exists because there's no denominator or negative inside a square root or anything like that. So we don't have to worry about does not exist. We do have to worry about when does this equal 0. So f prime equals 0. When? You set it equal to 0 and solve for x. All right. Can we solve for x there? Here I have 3 things multiplied together to be 0. That means each one individually we set equal to 0. All right, and what do we get? Well, okay, this one, x equals 0, is already solved for x. This is a critical number. E to the x equals 0. This we talked about last time, maybe the time before. E to the x, remember, is always positive and never equal to 0. So this right here gives me no solutions. We get no critical numbers from this part. From this part, we can solve that for x. We subtract the 2, x equals minus 2. So I have 2 critical numbers. They are 0 and minus 2. All right, let's make the chart with these values marked on it. All right, here's my chart. I have marked off the 2 critical values, 2 critical numbers, -2 and 0. Put them in like numerical order, right? Minus 2 should be to the left of 0. This is like a number line. And these are both points at which the derivative is 0. So we need to plug values in to the derivative to see if it's positive or negative in between. As always, I'm going to pick my favorite number to the left of minus 2, my favorite number in between here, and then my favorite number to the right of 0. So for the left side, let's do f prime of minus 3, say. Plug that in up here. I get minus 3 times e to the minus 3 times minus 3 plus 2. And I have a bunch of things multiplied together. Let's just think about the positives or the negatives. As always, you could plug this into your calculator, but not on our quiz or on our test. So look at the positives and negatives. -3, of course, is negative. What is e to the minus 3? Is that positive or negative? Remember your fact. This is like the first rule of Fight Club. E to any power is always positive and never 0. So e to the minus 3 is positive. Even though that's minus 3, yeah. E to the minus 3 means 1 over e to the 3, and that's positive. Anyway, minus 3 plus 2 is -1, so that's negative. So I have a negative times a positive times a negative. This is a positive. So I go positive right there. All right. Okay, that was the first one. Let's do in this range, your favorite number between 0 and -2. I think it's -1. So -1 times e to the -1 times -1 plus 2. This is negative. E to any power is always positive. And then -1 plus 2 is positive. So the answer here is negative. All right. And finally, your favorite number greater than 0. I use 1. I get 1 times e to the 1 times 1 plus 2. These are all positive. Positive, positive, positive. Makes this positive. All right. This is the whole chart. We're basically done with the work at this point. All that remains is just saying what the answer is. The answer, remember the question was, tell me the relative extrema and identify if they are minima or maxima. So remember how to do that. The relative extrema are these values, -2 and 0. So I'm going to say x equal -2 is a relative. And is it a maximum or a minimum? The first derivative test is what we're using here. You look at the signs here. If it goes positive to negative, that means the curve goes up until this point and then goes back down, which means this is at the top of the hill, which means it is a relative maximum. X equals 0. This time, this means the curve goes down and then back up, which means this is at the bottom, which means this is a relative minimum. There you go. That's our first example. I got only one more. It's a little tricky. All right, how about this one? 6x to the 2/3 minus 4x. 2/3, can you believe it? Let's do it. Let's not try and think too hard about this just yet. We are going to do the same procedure. We begin by taking the derivative and try to simplify as much as possible. So f prime of x equals. This derivative is, I suppose, ever so slightly weird. You do the usual thing with the exponents. I'm going to multiply the 2/3 down front. 6 times 2/3 times x. And then you decrease the power by 1. So you got to think, what is 2/3 minus 1? It is minus 1/3. And then I go minus, what's the derivative of 4x? It is 4. All right. Can we simplify this at all? Well, 6 times 2/3, you can simplify that fraction. I believe that's 4. 4x to the minus 1/3 minus 4. All right. I suppose you could factor the 4 out. That's not such a big deal. What is x to the minus 1/3? This is the same as 1 over x to the 1/3. I can write it that way. And then I suppose this becomes a 1 because I factored the 4 out, right? I hope you remember, what does x to the 1/3 really mean? I mean, you can continue to write it this way, but in your mind you should be thinking x to the 1/3 means the cube root of x, right? 1/2 power is the square root, 1/3 power is the cube root. So this is the same as 4 times 1 over cube root of x minus 1. All right. Actually, any of these formats here is probably pretty good. This is the derivative simplified as much as I can. All right, we got to find the critical numbers. That is, say when this equals 0 and also when this does not exist. All right, first let's set that equal to 0. F prime of x equals 0. This means I just set this equal to 0. 4 times 1 over cube x minus 1 equals 0. All right, can we solve for x here? Yeah, I think so. First of all, we can divide both sides by 4, and the 4 just goes away because 0 divided by 4 is still 0. So I got 1 over cube root x minus 1 equals 0. Okay, let's add the 1 over to that side to get the x by itself. 1 over cube root x equals 1. What should we do to solve for x here? I want to well, first of all, this is in the denominator, so I can multiply it over there to move it out of the denominator. This will be 1 equals cube root of x, right? If I multiply this over here, it becomes just cube root of x. And how do you solve for x when it's inside a cube root? We cube on both sides. That will kill the cube root over here. So it says 1 cubed equals just x. And what is 1 cubed? That's 1 times 1 times 1, which is 1. So x equal 1 is a critical number. This is a number when the derivative equals 0. Okay, We also must check, when does the derivative not exist? I think I got enough room to just say that right over here. F prime does not exist. Remember, what we need to be concerned with is it possible to get something weird like a 0 in the denominator in f prime of x? And actually, that is possible because there is a denominator here. So 0 in the denominator is what you're looking for. That would say, if the cube root of x somehow equals 0, can we solve that for x to determine which x has cube root x equals 0? Well, yes, you, again, cube on both sides. And 0 cubed being 0 times 0 times 0, this is 0. So x equals 0 is also a critical number. I have two critical numbers, x equals 1 and x equals 0. All right, let's make the chart. All right, I have two critical numbers. They're of slightly different types, right? X equals 1 is a number which makes the derivative equals 0. X equals 0 is a number for which the derivative does not exist. Okay. What do we do next? We choose numbers in betweens and plug them in. Let's see what happens. So I'm going to choose on the left side my favorite number less than 0, which would be -1. I'm going to do f prime of -1. Plug it in up here. It says 4 times 1 over cube root -1 minus 1. All right. The 4 I know how to handle. What is this in here? Remember how to do the cube root of -1. The cube root of -1. Of course, you can't do the square root of -1. That's a imaginary number. The cube root of -1 is okay, though. It is -1. That's because -1 times -1 times -1 is -1. So -1 cubed is -1, which means the cube root of -1 is -1. So this actually is 1 over -1 minus 1. And what is that? Again, I don't care what the number is so much. I care if it's positive or negative, although this is easy enough to determine fully. That's -1 minus 1. This is 4 times -2, which is negative, right? So over here I say negative. Okay, how about in between here? Between 0 and 1? What's your favorite number between 0 and 1? I'm going to plug it into the function. Now, this is a bit of a trick question. Ordinarily, in this situation, I would choose a half, right? Being my favorite number between 0 and 1. But I'm not going to choose a half. Check it out. I'm going to choose 1/8. Are you into this? Do you see why I chose 1/8? It's because I have to plug this in over here. And 1/2 is a hard number to take the cube root of. You would need to use your calculator for that. But 1/8, I know how to take the cube root of. Check it out. 4, okay, this is 1 over cube root of 1/8 minus 1. All right, what is the cube root of 1/8? I need some number, x, so that x times x times x is 1/8. The answer is 1/2. 1/2 times 1/2 times 1/2 is 1/8, right? That's why I chose 1/8 for this, because I know the cube root of 1/8 is 1/2. So this is 1 over 1/2 minus 1. Of course, that's 2 minus 1. These are positive and positive. So in here, the derivative is positive. All right? That's a little tricky. You got to be a little cute about how you choose this number, anticipating the fact that you need to plug it into the cube root, and not all numbers are easy to find the cube root of. Okay, one last number. To the right of 1. What is your favorite number to the right of 1? Keeping in mind, it has to be your favorite number that you intend to take the cube root of to the right of 1. I'm going to choose 8 because I like to take the cube root of 8. Ordinarily, I would choose 2, but I don't like to take the cube root of 2. I like to take the cube root of 8. So I'm going to choose 8. Let's do it. F prime of 8 is, plug everything in, 1 over cube root of 8 minus 1. And what is the cube root of 8? It's 2, because 2 times 2 times 2 is 8. So this is 1 over 2 minus 1. And what we have here is positive times negative, right? A half minus 1 is negative. So this is negative, so I put negative right there. All right. Finally, we are ready to say the answer. Now, when you have a DNE on there, you might be concerned. Maybe that's like an asymptote or something. Do I even say this one at all because the derivative does not exist right there? You have to think actually about the original function. Does this original function exist when x equals 0, and I hope you remember, the original function was f of x equals 6x to the 2/3 minus 4x, right? So does the original function even exist at all when x equals 0? Yeah, it does. You can plug x equals 0 in here, and you get 0. So x equals 0 is a valid point, even though there's a DNE here. We still should say about x equals 0. Is it a relative minimum or a maximum? Is a relative, what do you say? Well, you look at the signs. This says it goes down and then back up, which means this is at the bottom, which means it is a relative minimum. And x equal 1 is a relative, what do you say? It goes up and then back down, so this is a relative maximum. There you go. This is a weird example. Might as well check the answer. Remember, you can always check your answer by graphing the original function, so I'm going to graph this function right here. When I look at it, I do indeed see at x equals 0, there is a relative minimum. It's that pointy point. That pointy is what makes the derivative not exist there. And then x equal 1 is a relative maximum of a more ordinary type. Okay.